Let's see if I can get this right this time. This is my second time through it. I didn't waste too much on the first one, just about 2 minutes. But back here to try again. Let me get reset here before I bring it into view. But what we are going to begin looking at again, folks, is we are going to be looking at a little bit of application of the differentiation and integration of vector-valued functions. All right? The differentiation has some application, and the integration is going to have some application. And some of that application is related back to some ideas that we bring with us from earlier studies in calculus, Calc 1 and Calc 2, and then some of those, actually Calc 2 I believe, and then some of those ideas are actually some new ideas here. All right? And I should be careful there, they do relate back also. So what we're going to start with is looking at an application of differentiation where we can use differentiation to actually describe what we would call tangent behavior to a vector. All right. What we're going to look at here is the unit tangent vector. All right. Let me actually say it that way. I like that better. The unit tangent vector. All right. Given r bar, given a vector-valued function in n-dimensional space, right? What we want to remember is that vector-valued function represents either a curve or hypercurve in space, either a path or a hyperpath. And along that path, at points along that path, we can have tangent behavior, right? Either tangent behavior in 2 or 3 dimensional space or tangent behavior in n-dimensional hyperspace, where that tangent behavior is described by the derivative, right? Just like it was back in the case for Calculus 1, right? When we learned about the derivative, one of the interpretations we learned about it, when calculated for a function, it describes the slope of the line tangent to that function. Well, here, that slope is going to be interpreted in the vector context, and what we're going to be given is a description of tangent behavior with a tangent vector given by that derivative of our vector valued function. Now, formally, we don't typically present this tangent vector with its true length. That length can sometimes be, varies from vector to vector. And does have an interpretation within some context that we will get into later in our studies. But what we formally do when just talking about tangent behavior is we standardize, or what we say is maybe normalize that vector by shrinking it down and making it, or blowing it up and making it 1 unit in length, right? When describing a tangent behavior, using a tangent vector, we formally do it using what we call the unit tangent vector, using a vector that is 1 unit in length. And the way we do that is we divide that tangent description of behavior by the magnitude of that description. Remember, any vector divided by its magnitude is going to give us a unit vector description, a vector that's 1 unit in length. If we divide out the magnitude, if we divide out its length, we're left with a vector that's 1 unit in length. All right, a unit vector. And that's what we see happen in our definition here. If I bring the definition up into view, right, here's our definition for vector-valued functions. Well, and the corresponding unit vectors. Given r bar t in our n-dimensional space, the unit tangent vectors for r bar are described by the following result. And they are themselves a vector-valued function. In the case of parameter t, it is in the context of parameter t in its description of unit tangent behavior. And this is what we often denote it as, capital T bar of t. All right? Where how do we calculate that? We take our derivative of r bar prime of t, and as I had highlighted, divide by its magnitude. This r bar prime of t describes tangent behavior. Dividing by its magnitude makes that description of tangent behavior a vector that is 1 unit in length. right? And remember, our magnitude calculation is essentially the square root for the sum of our components squared for the given vector whose magnitude we're calculating. We'll see an example here. Consider finding t bar of t, capital T bar of t, the unit tangent vector for the vector valued function given here, r bar of t equal to t comma t squared, a familiar looking vector valued function, the one that looks a bit like our classical parabola, or is our classical parabola, but described parametrically using a vector valued function in two-dimensional space. All right. Well, what we're going to need is the derivative of this vector, which is not difficult to find. The derivative is the derivative of the components, so that'll be 1, this will be 2t. And then we're going to divide that by its magnitude. All right? And let's take note of how that all forms. If I bring this up into view, all right? Note, for r bar of t equal to t comma t squared, the description of tangent behavior given by r bar prime of t is 1 comma 2t. It's the derivative of the components for this vector. The derivative of t is 1, and the derivative of t squared is 2t. All right? And if we think about the magnitude then of this vector result, r bar prime of t, it is the square root for the sum of the components 1 squared and 2t squared. It is the square root for the sum of the components squared from the vector whose magnitude we're trying to find. If it's three-dimensional, we would add in that third component squared under the radical. In this case, 1 squared is 1, 2t squared is 4t squared. And we end up with the magnitude description along this curve r bar prime of t given by the square root of 4t squared. If we're at any value at t, we can plug it into this magnitude description to come up with the length of the tangent vector at that point in at that value of the parameter t. All right? We'll see that noted here. So if we think about the unit tangent vector, it is nothing more than taking our vector r bar prime of t and dividing out from it this magnitude description, the square root of 1 plus 4t squared. Where if I distribute, now this is a scalar multiple, right? We could actually think of that, if we wanted to, this way, a scalar multiple of this vector, where I can distribute that across the components and come up with this description of my unit tangent vector with respect to t. Where now what I can do is at any point along the curve r bar of t, plug that point ft into t bar and get a description of our unit tangent vector. So for instance, at t equal to 3 on the graph of r bar of t, right, the unit tangent vector is described by t bar of 3. You just plug 3 into this formalization for t. 3 into the denominator, this becomes 36, plus 1 is 37. So you have 37 under the radical in each case, in each component. So it's going to be 1 over the square root of 37 for the first component. And then if we plug 3 in the numerator here, that's going to be 6. So it'll be 6 over the root of 37 for the second component. 1 comma 6 describes tangent behavior, but dividing it by that square root of 37, the magnitude of that vector described by 1 comma 6 makes our tangent description of behavior a unit tangent description of behavior, a vector that's 1 unit in length in its description. If we look at an illustration of that, I do give an illustration of that down below here. You make it a little bigger. This graph is a bit truncated. Notice this is not the origin in our picture. And our graph is of that square function, but we're only looking at a very small portion of it along the x-axis, so you don't really see much of the curvature here. So it is truncated, and we are, looking at just a very small portion of it, so you don't quite see its entire curvature. Here's the direction it's moving. It is the black graph given here. That is the graph of r bar of t. And right at this point is where we're at when t equals 3. We would be at 3, 9 on that vector description of position. Now at that point, there is a description of tangent behavior, and that is what's being illustrated by the green vector here in this illustration. You can see it's barely noticeable. That's why I did make it a different color here. Right? But you can certainly see that it is pointing in a tangent behavior, right? Or it is behaving in a tangent behavior to the curve at this location along the curve. And what is unique about the length of that vector? Well, that vector is only 1 unit in length, right? This graph is at a scale where this is 1 unit in length in that scale, right? At least it should be. I will tell you, it's a little morphed in scale. 1 unit along this axis, you can see, is not equivalent to 1 unit along this axis. So it is a little morphed in scale. So actually to see it measure 1 unit in length, we won't be able to do in the graph unless we were to scale these two axes exactly the same, which I didn't do in this illustration. But what I am illustrating is in the morph scale, it is 1 unit, and it is indicating that direction of tangent behavior. And one thing to note about that direction of tangent behavior is it points in the direction of the parametric curve, in the direction of forward orientation is the direction indicated by that tangent behavior, right? We might say if this was an object moving along some path in space, at that exact moment in time, that is the description of forward motion for that object. Certainly, there's also a description of slightly turning, upward in the space at this point in time to present the slight curvature to the graph. But this specifically would be the description of forward motion at that point in time. And that forward motion kind of rotates itself through that space. All right? Folks, this is unit tangent vector. This is the first application of differentiation for vector valued functions. We are actually going to take this a step further in our descriptions of motion in space and have an interpretation for this derivative of a position function. And it's going to relate back to what we understand from Calc 1. So, hang out for that. I will be presenting that to you soon enough. I have, I think, one more quick video to give you before we get into that stuff. And I don't think I'm going to get that video out tonight. You're probably going to see that the day of class. It's already 10:30 at night and I'm getting tired and I got to get these things uploaded and work on 1 or 2 more items. So, with that said, I will close this down and I will see you all in the next class period.